Check, check. Hello, Rachel. Wait. They work better when they're turned on. All right. Not that anybody talks in this class. I probably don't even need them. I just need a mic. All right. It's funny, I'm still in the habit of putting up, I don't know if you can see this, like I put up the, the grid just in case somebody like raises their hand or something, but not really necessary here. I literally like 30 seconds ago, I was trying to get some examples ready for today. So I just posted in D2L under the, where did I put it? It's under, whoops, hold on. Under this week in D2L, I just posted it. So if you want to follow along, if there are no homework questions or practice questions, I just posted under the content browser. This is our last new stuff. Our last new stuff. Whoops, not finals week. I did it again. Week 15. There's at the very end there, chapter 12 and 13, extra practice, if we have the need for it today. Reminder of what we have left is not much. We just have one last week of new content. That's this week. Yeah, so you have some homework due Wednesday. And then your quiz, the last quiz on Friday, or Friday. And then we have one last unit exam next week. So far, let me remind you here, pull up the updated syllabus. The final exam, normally we were going to have the unit exam this week and the final exam next week. And we lost a week. They canceled a week of classes the week of March, I don't know, 5th, something in the teens. So what I asked my dean for approval from, and she said it was okay, we could, because of the design of this class, it's so cumulative, we could make the final optional. So if you do not do the final, it will just be left out of your grade, not a 0, but just left out. You'll only have 85% or something like that. So it will not affect your grade whatsoever. And the only thing you will have left, this should be exam 4, will be exam 4. We're going to have one last class next Monday, and then we'll release that last exam Tuesday morning, and it'll be due Wednesday afternoon. If you would like to take the final because you think it might help your grade, you are welcome to do so. If you choose that option, the final will count toward your grade. So you better be sure, if you had like a couple of bad exams and then you got in a rhythm, or you had like the last exam maybe was rough and you think that would make a big difference, that's fine. But you want to be sure that your grade will improve on the final. To be clear, the final is not the entire semester. It's just chapters 1 through 9. Didn't make sense to have a exam over chapters 10 through 13 and then include that stuff like the next day or the next week or whatever. So that the final was originally going to be chapters 1 through 9. So if you want to do that, that would be, you'd have to let me know. Boy, when should you let me know? By Friday, maybe, of this week. If you want to do that, and I can get that ready for you. I think most people probably will not want to, because it's hard to do better on a cumulative test than on other tests, but it is your option. Okay. Are there any questions about schedule and what we'll be working on for the last week and a half here? Any schedule related questions? Okay, I'm going to open up the chapter 12 practice here too. That's what you'll be doing your quiz on. And so we can go over some questions if you have any on that. And if not, like I said, I did just upload, this is behaving really oddly here, what's going on? I did just upload some extra practice with a couple of examples there, and we can do that instead. So does anyone have any requests, homework questions or practice questions that you wanted to ask about? Ooh, make sure I'm recording. Yeah, okay, I am recording. Any requests? Not seeing any. It's Monday, so maybe there'll be more on Wednesday. Okay, so let me jump over here to the extra practice, which again, if you want to follow along, is in D2L. Why do I have two D2L windows open? I'm not sure. Okay, so it's in D2L under Unit 4, Week 15 at the very bottom. There's some extra practice. It's a Word document. When I wanted to do one from each section. So we have, maybe I can even label, whoops, that's not it. That's the regular practice. It is the extra practice. So we have 12.1. 12.1 is about goodness of fit. Let me put a little note here. This is about goodness of fit test. So what that's testing is, you have some data, you have some counts, and you're wondering, do these fit a specific distribution? How well do the data fit the distribution? And there's usually some claimed distribution. How well do they fit the claimed distribution? And so what StatCrunch does is it calculates the actual counts, but it has the actual counts, and it compares them to the counts that should be expected. And it calculates a chi-squared statistic, chi-square. Same as the variance, that should sound familiar. That's from the variance stuff from chapter 9 and 10. So here's what we're gonna do. I'm just gonna copy these counts and go over to StatCrunch and open a new StatCrunch window, because I have the health behaviors thing here. So I'm gonna just go, how do I just click on StatCrunch? I just want a new blank window. Open StatCrunch, there we go. And I'm gonna click under the variable 1 and hit paste. If you paste down here, then the color, like it gets confused. It doesn't know it's a title, so you go up here. So on the test, we will have a question like this. The counts will be provided, or they'll already be in the data file for you. So you either copy and paste them, or they're already in the data file. Okay, so the goodness of fit test is one of the tests. You can see it there under, I feel like I need to zoom out here. It's like, oops, it's too small. What is happening? It won't let me zoom. There we go, be in the right spot. Okay, stat, and then goodness of fit. So this is goodness of fit, and we're doing the chi-squared test. It looks like chi, but it's chi. So goodness of fit, chi-squared test. There are two options here, and it's a little confusing for students. So you're observed, those are the actual counts that you have. And so, oh, I didn't even explain the problem here. I'm totally getting ahead of myself. So this doesn't make any sense. If you watch the video, you know there's this thing about, does the M&M, the color of the M&Ms fit what the factory claims? So I found some Skittles. My kids got some Skittles. Of course, I could have just made up these numbers, but I couldn't do that. So I actually wasted time counting the colors of the Skittles. It's totally pointless, because this is just an illustrative example. But anyway, they're the actual counts of Skittles. And so I don't have any proposed distribution. So I'm just going to say, like, well, what if we wonder is there enough evidence to say the colors aren't distributed equally? So kind of what I would expect is that I would have the same or close to the same number from each one. Now here, obviously I don't. For some reason, there's a lot of pink ones. They're not really, they're kind of pink. I don't know, it's whatever, oops, I dropped it. Whatever color this is. You see that? I don't know, it's kind of pinkish. I have no idea. So whatever color that is, there was already a red, so it's not red. So that one obviously had like twice as much of the other. That could have happened randomly. So it doesn't look like they're all the same, but what the chi-squared goodness of fit test will do is it'll say, is that a statistical deviation from equal for all? So that's the question. The key here is that last part, to say the colors aren't distributed equally. So back to the test in StatCrunch, you have two options. You can tell it the actual expected counts, or you could say the second option, that's what we have here, that all the cells are in equal proportion. I feel like you have, in the practice, you have one of those and then you have a different one. Okay, so you have one where they're all equal, and then you have a different one where they're not all equal, and you actually have to calculate the expected values. This is the M&Ms. So what you'd have to do there, and I don't remember which one, CLV, you have to use these percentages and manually calculate, oh, if I have 100 M&Ms or whatever it is, I would expect 21 blue, 21 orange, 20 green, 14 yellow, 13 red, 12 brown. You see how I'm just like using the percentages? So you'd have to manually calculate those. So there's two options in the StatCrunch here. You either check, I expect all the boxes to be equal, or I have actual expected ones that you either were provided or you figured out yourselves. So we're going to click all cells in equal proportion. And I'm just going to hit compute. There's really nothing else that we do here. There is obviously other stuff you can do. We're not going to do it. So again, it was stat, goodness of fit, chi-square. And then you select your counts for the observed, and then we're selecting the expected that all cells are in equal proportion. And we'll hit compute. And you can see how, do you see how it got 13.8 was the expected for each one? All it did was take the total number of 69 and divide by 5. And so that's what it expected. So what it's going to do is it's going to look how far is each one from the expected, and then it's going to calculate this chi-squared statistic. Okay, so let me go back to the extra practice. This is a chi-squared goodness of fit test. So let's do our steps. The null hypothesis is that, really it's kind of weird here, but the counts fit the claimed distribution. In other words, the colors all have the same number in this case. Now, it's not always going to be that they're all the same. That depends on the problem. For the M&M problem, the alternative is not that the colors all have the same counts. It's that the colors fit the distribution that the company says. Okay, then the alternative claim is just the opposite. The counts don't fit the claimed distribution. I'm adding more here, but just kind of to be clear here, the colors don't all have the same. Same number. All right, our alpha, we're kind of using our standard here, 0.05. And then we have our test statistic is the chi-square. That was in StatCrunch. It's like 8 point something, if I remember correctly. We'll call it 8.32. Oops, yep. One comment about the exam here. I'm gonna ask for all these steps on the exam. And so for the null and alternative hypothesis here, for this particular example, words are best. There's no symbol here. It's not that I'm wondering, is the mean like mu equals 8? No, it's just, do they fit the distribution? So words are the null and alternative. For the test statistic, I want the actual name of the statistic. It's a chi-square, and I want the value. Okay, then a p-value here, it was about 0.08, 0.081 maybe, 0.081. something like that. 0.08 is fine. So reject or not, I guess. We did our votes, right? You know how to do your votes, yes or no? Remember how to do the yes, no? You go up to, go to participants. I think this is what it looks like for you too. I think it's participants, right? And do yes, no. Why don't you vote yes or no to reject? Reject the null hypothesis, maybe? Yes, no? What do you think? Awesome. You all are great. So everyone said, well, everyone except one, but everyone who voted said no, which is correct. That is correct. All right. We do not. It's close, right? Though it's close. So do not reject the null hypothesis. Okay, I have a question for you. Suppose you are a researcher and you really think that the colors aren't all the same. And you want to, like, this is so close. Can you think of some options that you have at your disposal as a researcher if you wanted to research this further? And it's not that you can't, it's not that you want to like keep researching until you get the result you want. But suppose you're really skeptical of this and you want to do another, like you want to really research this. So what are some things you can do as a researcher to investigate the distribution of Skittle colors? Any ideas? Yeah, Brittany is right. Use a larger sample size. So basically, like one thing you can't do is repeat it over and over and over, because here's what can happen. Here's what can happen. If you repeat this 20 times, one time it might just randomly not fit. So what you would really want to do is, like, suppose we did this again and we did it, let's suppose we did it 10 times the sample size and we got exactly the same distribution, which is not guaranteed. But suppose it was 110, 230, 110, 140, and 100. So suppose it was 10 times with this huge bag of Skittles and we got exactly the same distribution. Well, watch what happens if I'm just going to edit and then hit compute, do the same thing. Now the p-value is really, really small, because now that difference from 230 to 138 is really big. So that one that stuck out really sticks out now, whereas it didn't with the small sample sizes of 11, 23, 11, 14, and 10. I'm just going to actually not close this one, but just do it again. Now you got to be careful as a researcher, because there's no guarantee you're going to get the same distribution, but it'll be at least more like satisfying to you. You know, if you do it and you get another, if the p-value is still high, well, then maybe they are all the same. I don't know. But if you're really skeptical of it, you could do and get like more bags of Skittles and get a huge count of Skittles and see if they really do all fit the distribution. Because I'd be pretty skeptical, right? 23 is a big jump. But the problem is we only had 69 Skittles. It's not very many. So that's why the p-value was small, but not small enough. So we would say no, do not reject. And now here's the thing. This does not mean that the colors are all the same. I don't know if you're just watching or if you're following, type in this yourself. Can you take a minute and type the conclusion here? It's tough. Again, when we don't reject the null, it does not mean that the counts are all the same, that the colors have all the same. That's not the conclusion here. So see if you can type that up, and you could just type it in the chat if you want to. But the conclusion is hard on this one. I think so, at least. I have these Skittles here. They're not even tempting. I don't even like Skittles. Put them all like flavored sugar. Yeah, Brittany is right. Do you see her wording if you have the chat up? There's not enough evidence to say, oh, no, hold on, there's not enough evidence to suggest, oh, okay, good, you're really close, you're really close. You started out, I was a little distracted there, because you started out great, there's not enough evidence. But we're always look for evidence for the alternative. And we were trying to see if the counts weren't all the same. So there's not enough evidence to say that the counts aren't all the same. That's what we were, you see how confusing that is? So there is not enough evidence at the 5% level of significance to support the claim, and this is where you have to put the alternative. It's always the alternative, that the colors don't all have the same number of Skittles, or however you want to word it. I like the way that Brittany worded it. It made a little more sense than my abstract colors don't all have the same number. That's really awkward phrasing. But again, the final conclusion is always about the alternative claim. Is there enough evidence to support the alternative? So we did not reject the null, so we do not have enough evidence to support the alternative that the colors don't all have the same number. I feel like statistics is full of double negatives. And unlike in your English class, it makes a difference. Because it's very different to say there is evidence to support the claim that the colors are all the same counts versus there is not evidence to support the claim that the colors aren't all the same. Statistically, those mean different things, even though grammatically it sounds like they're the same. So you get a lot of, in this, when you don't reject, you get, kind of looks like a double negative. But this is a classic goodness of fit test. You have some counts. You do in StatCrunch, again, you do the stat goodness of fit, chi-squared test, you pick your counts. Either all are equal, you'd have to be told that, or you're given some information about what the expected counts are, you do those, you hit compute, and then you interpret, oops, yep, we all do equal. Then you do your interpret, you have your test statistic is a chi-square, and then your p-value. Okay, any questions about this goodness of fit test? Put the chat window by the camera so it looks like I'm looking at you. Anybody know why I'm at this background, by the way? You recognize it? It's May the 4th. May the 4th be with you. Star Wars Day. Come on. I'm on the Millennium Falcon. Okay, sorry. Moving on. All right, so the first test is the goodness of fit test. That's 12.1. 12.2, there's really two tests in here, but they're the same thing. It's for qualitative variables, where you have, remember contingency tables? You're actually going to learn that bottom thing on a contingency table that you never really understood before. So on the it's about determining if two qualitative variables are related. There's also, I can show you in the content, I have a shortcut link here. So it is two tests, the test for independence and the homogeneity of proportions. It's like a lot of syllables, but they're really the same test. So it's determining whether two variables, you have rows and columns because they're qualitative variables, whether they're independent. So the null hypothesis, you're going to assume that they're independent, and you're going to test the claim that they're dependent. There's some relationship between them. And if you look at the result here, if we go down to the chi-squared test for independence, here's the way to do it. And then if we do the other one, the test for proportions, it's the same process. The procedure is the same. I can explain why once we get in there, but they're really the same procedure. So I only did one example because it's the same procedure. So to find an example, I had to think of two qualitative variables that we think might be related somehow. And the health behaviors in school-age children has a lot of qualitative variables. So if you want to open that one up, here I was looking at overall health, and there's like a rating scale there. And then I thought, I don't know, maybe like who the responsible adult is. You know, is it mother and father? Is a mother only, father only, grandparents, someone else? Like there was like a few different choices there. And so we're wondering if the student's overall health is related to who the responsible adult is. And I've tried to be a little vague here for the purpose of today's class. I'll be more specific on the exam, but I said to investigate this relationship. So I kind of want us to do that, kind of see what we can garner before we just jump in to do the test. So I have the health behaviors here open, and let's first start with a contingency table. I'm going to go stat, tables, contingency, and with data, because we have each row here is a student. So we have the raw data here with data. And I'm not going to worry about which one's row, which one's column. It doesn't matter. We were responsible adults and overall health. Responsible adult, overall health. If you want to follow along with me, you probably should do the same as I'm doing. Otherwise, it'll be confusing. But if this is you on the exam, don't sweat it. Just pick one and go with it. Don't sweat which one is which. So I'm going to hit compute. Looking at these counts here, I don't know if you remember, I actually gave you a problem when we were still in groups, and I said, like, what do you notice from the relationship? And I kind of wanted you to see that you can't really see anything. Like you can't, it's like impossible to tell. So what you need to do is you need some kind of row percents or column percents. So why don't we do this? Why don't we look at how the overall health is distributed and then compare that distribution by who the responsible adult is. So we're going to do the conditional distribution of overall health by who the responsible adult is. So you remember this is where it was column percent or row percent. So let's do a little vote. We're going to do yes, no. Yes is row percent, and no is column percent. And if you want, you can guess and go in and try and see if you're right and come back. So, and then put your answer later. So the first things here, first, let's do a contingency table. And I'll restate my question. So contingency table, I'm just going to copy just the table part here. Looks like I need to be like on a new page or something. I think I can just delete this. That all fits. Okay. So can't really see anything here. Okay, next. Let's do the distribution of overall health by the responsible adult. So question, would this be row percent? And I want you to check the yes box for that, or column percent. And that'll be the no. And go ahead and just, you don't need to answer right now. You can, like, if you think which one it is, try it out, see if you're right, come back and answer. If you're not sure, just kind of pick which one that you think it is. I'll give you a minute to try that. Maybe I can do both. Options, edit, row percent. Wait, was that the first one? Row percent, yeah, row percent was first, so that's yes. Okay, so there's yes, that's row percent. Okay, can't see. All right, stat, what was it? Tables, contingency with data. We did responsible adult for rows and overall health, and now we're going to do column percent. Okay. Those are the two. Okay, so we're voting yes or no. Yes is the first option here, row percent. And again, we're looking for the distribution of overall health, the distribution of overall health by responsible adult. So you have yes. It's not really like yes or no, but it's really, that's just the two options we're going to do in quick vote. So do you think it should be row percent or do you think it should be column percent? Which one of those gets you the distribution of the overall health by who the responsible adult is? All right, lots of green, lots of green. It's hard because you all can see what everybody else is doing too, right? So like once you see a few greens, you're like, I don't know. So you are correct though, that is exactly right. So the reason why is if I look for both mother and father, this tells me the distribution of overall health. And then I go down a row, it tells me the distribution for the next category. And so this gives me the distribution of overall health. So I'm going to close the column percent. It would be row percent. So now let's just look at this. Let me copy this. And let's see what this tells us. Let's see. It would be row percent. Row percent. Okay. Let's see what this tells us. Now, I don't know if you remember, this is where we kind of deleted the counts. I don't know if I want to go through all that for all of this. That's a little tedious. But so we're focusing on the percentages. So what do you think? Does the responsible parent seem to affect the overall health distribution? You notice anything? Anybody notice anything? Do they all seem about the same? Or does who the responsible parent is seem to affect the child's overall health? Yeah, Brittany's looking at them like, yeah, they're all fairly similar. You got a small, poor, right? So small percentage here, 2, 3, 4% over here. Ooh, here's 5% other. Fair is about 20. Good is about 50. Excellent is about 20. But here's where it kind of popped out at me where I was a little skeptical. Because I see 28.5% here for both mother and father. And then for some reason, mother only was like 25%, but mother and stepfather was 21.6%. That seems pretty different from this. Now that's just one cell. It's still kind of hard to tell. They definitely look fairly similar. Nothing really jumps out at me, but I'm a little skeptical of this. So if I had to guess here, I would guess, especially because of the sample sizes, the counts here are really big. There's 12,000 students. I would guess that it's probably statistically different. There's probably a relationship there statistically, though to be honest, practically there's not a huge difference. But you can see here, mother and father versus father only. Father only, mother only does pretty fine. Grandparents, mother, father, stepmother. This is interesting here. I don't know enough about this. And this, to be clear here, this is not a causal relationship here. Moms who remarry might tend to be maybe lower income, and so they remarry to help support the family. I don't know. So there might be other reasons why. It's not saying, I don't want to like put this bad connotation on stepfathers. So it's not a causing here, right? It's not saying that relationship is causing it at all. We're only looking for relationships between these variables. We can't say that one thing causes another. We could say kids with excellent health tend to be easier on the parents, so the parents stay together, right? That makes as much sense. So there's no causing relationship here. It's just is there a relationship between the variables? So I would just say, again, this is not a test question. This is just an investigation for us in class. To Brittany and Justin's point, they all seem to be distributed relatively similarly. It does look like mother, stepfather is related to an overall lower health rating. But we can't statistically say that that's true. So now let's do the test. Let's do the test. The null hypothesis, and the null hypothesis is always that they're independent. So responsible adults and overall health are independent. And again, on the test, I want you to state that in words. That's a words thing here. You're going to write that in words. And I don't want that the null hypothesis is independent, like that word only. Like, be specific. What two things are independent? That's be specific. And then our alternative is that they're not. You could say that they're not independent. You could say they're dependent. You could say they're related. Some word like that. Responsible adults and overall health. I'll just put are related. Dependent. There's some relationship between them. We said test the hypothesis at the 5% level of significance, like usual. I feel like we do that every time. It's just really common in statistical research to use the 0.05. Okay, test statistic. We have to get that. And then p-value, we got to get that. So let's do the, go back here. Did you notice, by the way? Did you see it on the bottom? It's down there automatically. In fact, when you go to options, edit, there's a hypothesis test, and the one that's kind of selected by default is this chi-square test for independence. Now, you probably don't remember, but some of you back in chapter 4, some of you copied and pasted that in your work, even though you had no idea what it meant. Zero. But now you do. And I remember talking about it and saying, we will learn what this means. We will learn. And today is that day. This is the section. So there's our, this is a chi-squared test statistic. So it's 108.1. It's really big. Test statistic, chi-square. It's really big, 108.1. P-value, I believe, was off the charts, right? Less than 0.0001. I'll talk about why it's so small, even though they look relatively similar. I'll talk about that in a little bit. Why don't you finish up? What do you think we should do for the test? Reject null hypothesis, and then the conclusion. Why don't you type those up? Ooh, no, let's do what we did. No, let's do what we did. Let's vote yes or no. Let's vote yes or no to reject. I think we have this idea down by now, but just to make sure. Why don't you give me a yes or no? Yeah, good. Okay. Everybody's got this. We know small p-value we would reject. So excellent, excellent, excellent. I think I get a little, there's one of these things as teachers, we talk about gauging whether everyone understands what's going on. And one of my problems, and this is really common when you're in a regular face-to-face classroom, is you look and you see like 3 or 4 people making good eye contact and nodding, like they get it, they seem to get it at least, or they answer the questions. But there's like 24 other people that maybe get it, maybe don't. And so right now, we have 6 people here, and everybody's following along and doing the right things, and it's looking really good. But there's 22 other people out there who maybe are watching the videos, maybe not. So hopefully they are getting it as well as you all are. But yes, we do reject the null hypothesis here. So again, we're looking for evidence for the alternative. So we would say there is enough evidence, and capitalizing is, you don't have to do that, but just kind of pointing out for us. There is enough evidence at the 5% level of significance to say that maybe let's word it more like English. Who the responsible adult is in the family is related to the child's overall health. So there's clearly a relationship there. So there is enough evidence at the 5% level of significance to say that who the responsible adult is in the family is related to the child's overall health. So there is a relationship there. The reason why that p-value is so small, even though, as we noted, the distributions look fairly similar, It's the sample sizes. The sample sizes are really big here. And so small percentage differences end up becoming statistically significant. And one of the points you might have as a researcher is, okay, there's this difference here. Is that important? Is it like practically a big difference? It's a statistically significant difference, but like, is that going to make a difference in a child's life? Where if I know a child is living with a mom who's remarried, is that worth me maybe as a school guidance counselor or nurse kind of keeping an eye on that child, making sure the child's healthy, kind of like maybe doing extra checks with them? So I don't know how you feel about that. It's about 6-7 percentage points lower our rating as excellent. And then look here, you see the FAIR. You see how much higher the FAIR is for the mother with stepmother or stepfather. So to me, that's a pretty important and relevant difference. And so for me, I'm not a nurse, I don't know, but to me, it seems worth saying, you know what, maybe that's something that we should keep on our radar. And we know on average, children who are living with their mother and a stepfather tend to have poor overall health. So we'll keep an eye on them more and kind of keep watch over them and maybe send some extra information home or something. I don't know, but that's the kind of thing where you can get really small p-values with really large sample sizes, and it might not be that different. In this case, I do think it is a relevant difference between the two categories. So that is a chi-squared test for independence. It's a chi-squared test for independence. Any questions on that one? Okay, last test. This is in section chapter 13. We're just through 13.1. It's kind of weird. It's called an ANOVA test, analysis of variance. It sounds really cool. In fact, we are doing what's called one-way ANOVA. That sounds even fancier. So what's confusing is it's called analysis of variance, but it's for comparing means between multiple populations, more than two. So we have a test already for comparing two means, right? That was chapter 11. We just learned that last week. We had a mean difference, but we also had two independent samples and comparing their means. This one is for comparing the means between many different populations, maybe 4 populations. You want to know, do they all have the same mean? The null hypothesis in these is always that all the means are the same. That's the null hypothesis. And then the alternative, it's not that they're all different. It seems like that's the opposite of it. But you can break all them being the same without them all being different. All you need is one that's different. So the alternative is that at least one mean is different. At least one mean is different. So either all the means are the same, or there's at least one mean that's different. In this example, we're looking at individuals' height and the thoughts on their body. Might be a relationship between those, but height is a numerical thing. Like it's a calculation, right? You get your height, and then thoughts on body is qualitative. So what we're going to look at is we're going to wonder, okay, if I look at these different categories for thoughts on body, do they all have the same average height? Maybe people who have more positive thoughts on their body are taller, or maybe not. Maybe they're shorter. I don't know. So we're gonna compare those. And we have 5 minutes, so I need to stop going off on tangents. Alpha equals 0.05. Oh, let me go to I need a new page here. Insert page break. Okay. And again, we have our test statistic. And then statistic singular. And then we have p-value, and then we'll do our p-value equals. Okay. So again, for the ANOVA, this is where you're comparing means, and the way you're going to know this, because you're going to also have comparing two means, it's going to be on the same test. the way you're going to know, the problem might tell you to use ANOVA, use analysis of variance. Or the way you'll know is when you have means from more than 2 populations. That's the way you know it's this one. Okay, and in that test, the null is always that all the means are the same, and the alternative is always at least one is different. We've actually done this before, kind of. So, wait, what were we doing? It was height by, so you know what, I'm getting ahead of myself, because I said to investigate this relationship. So we've done this before. We did it with some box plots. So let's do graph box plot, and let's graph height, and we're going to group by the variable we're interested in. Thoughts on body. That's what I said, thoughts on body. And I'm going to just check off outliers for now, and I'm going to draw my boxes horizontally. So I should, again, I'm trying to get a box plot of height to see how height is distributed, but I'm going to break it down by their thoughts on their body. So let me hit compute. Okay. All right, that's kind of what I was hoping for, a bunch of box plots. Okay, interesting. I should put a title. I always got to put a title. Thoughts, no, height by thoughts on body. Okay. Looks good. Copy image, go over here, paste that in here. So what do we think? We only have a couple minutes here. The test is really fast, but that's okay. So based on those plots, does the mean height appear to be different? I have an idea. How about you? Do you have an idea? Does the mean height appear to be, would you say it's the same for all the thoughts? Or does it seem like there might be some differences between some of the groups? I tend to agree with you, Daniel. Did you have like one in mind, or like a one pair in mind you were looking at? Yeah, group E. So this much too fat. And their mean seems to be about exactly that. This is the median, of course, but seems to be about exactly the same as a bit too fat. But like if you compare those two with the opposite end, the ones that are much too thin, it seems to be like the median is really a lot lower for the much too thin. They tend to be shorter for the much too thin. About the right size and a bit too thin seem almost identical. So it's interesting, there's like these pairs of ones that are identical, but they don't all seem to be the same. So I agree, on the surface, the much too thin group appears to have a lower height, lower mean height than, and we'll just use the ones at the other end of the spectrum, the much too fat and a bit too fat groups. So that's just eyeballing it. That's not a statistical test, but that's just eyeballing it. And we've done some analysis kind of like this before. We did actually confidence intervals before too, and we looked to see if the confidence intervals overlap. We're not going to do that right now. Let's finish with the test. We have 0 minutes left. It's very fast though. So it actually has its own submenu, stat, and there's ANOVA, and we're doing one way. Stat, ANOVA, one way. And we're doing height. Oh, it's in the, actually, sorry, they're all in the single column. This, you can compare multiple columns if you have your data in each one has its own column, but we have height in a single column. So the responses are in height, and then the factor that we're looking at is the thoughts on the body. Thoughts on body, there it is. Thoughts on body. So we're doing one way ANOVA, values in a single column. Our responses we're looking at their height, and the factor is thoughts on body. We hit compute, and we get an F statistic here, F stat. The stuff up above is just what the sample means are for each group. Down here on the bottom is the test results. We have an F stat is like 17.2. That's our test statistic, F is 17.2. P-value is very small. Again, it didn't look like a huge difference, but these were really big sample sizes, you know, like 11,000 students. So very big sample sizes. So we would reject the null hypothesis and finish with there is enough evidence at the 5% level of significance. Oh gosh. To say that at least one mean is different from the others. Or maybe it makes more sense to say that the means are not all the same. Right? In other words, there is a different mean height between the various thoughts on body responses. That's a little more advanced comment there. You wouldn't need to have that on the test. What I'd be looking for, if I bold, what I'd be looking for is this stuff here. All right, that is the last test. And that's it, just 3 new tests. You have the first one, goodness of fit. You have the test for independence. And then this last one is the analysis of variance. And that is it for the course right there. Any last questions on this last one? All right, I'm not seeing any. I'm gonna save this. I remember to post, make a note to myself. Post solutions. All right, and then Wednesday we will focus on questions. I can make some more examples if you want, but I'm hoping you'll have started the actual practice by Wednesday, and so we can take Wednesday up working on questions from the practice, getting ready for that very last quiz. We can also spend some time on Wednesday doing some review if you want. We'll have Monday for that, but we can take some time on Wednesday for that as well. Okay, I think that's it. Last call. Any questions before we sign out? All right. Thanks, everybody. I'll see you Wednesday.